Yeah, we want to know how thick the ice is on average, and for this you have to take quite some measurements to get a statistically reliable measurement. That's the one thing. But then we are also interested in the spatial, so thickness with distance, because we have coincident satellite images which show individual areas, and we want to assign certain thicknesses to the individual areas in the satellite image. I suggest we do this, one after each other, or one method after each other, and normally it would be more efficient, of course, if we introduce to the drilling and then one team of us immediately starts drilling, but then they wouldn't see how the other methods work, so we just demonstrate each method first and then we go into production. So this is really where you have to develop some kind of understanding of what the instrument actually does. And in general, the instrument is a conductivity meter, so it measures an electrical conductivity, which is measured in units of Siemens per meter, which is just the inverse of ohm meter of resistivity. And it does do the measurement of conductivity by means of electromagnetic induction. And the way this works is that there is a transmitter coil, so a coil of copper wire in the one end of the instrument, and another loop, a receiving coil at the other end, which measures the strength of the field generated by this transmitter. And the field generated here, of course, is propagating directly to the receiver on the one hand, but on the other hand it is penetrating through the ice into the seawater underneath, into the seawater underneath. And because the sea ice itself is highly resistive, has a conductivity of approximately 0, the field penetrates through the sea ice almost unaffectedly, while in the seawater it induces eddy currents. And that is because the seawater is saline and so conductive. And so these electrical currents induced by this slowly varying EM field, it has a frequency of 9.8 kilohertz. These eddy currents in turn induce a secondary electromagnetic field. And this electromagnetic field penetrates up through the ice again and is sensed by the receiving coil as well. And the primary field, which is directly going from here to there, is compensated internally. So the signal we obtain is the strength of the secondary electromagnetic field. And that field strength is directly related to the conductivity of the water and to the distance of the water between the instrument, the distance between the water and the instrument. And if the instrument rests on the ice like it does here, the distance to the water, of course, is identical to the ice thickness, and this is how we can measure ice thickness. Yeah. So now we only have to wait for the details. So, I mean.
But in this case, we're concerned with point measurements at given points along our transect at every 5 meters. So we're just going to be measuring points.
Push measure here on the Trimble unit, and it takes three readings and averages them for the northing, which is the north, how far we are from the equator, the easting, which is how far we are from the prime meridian, and elevation. And that's about it. And once we compare it to sea level, we'll know the thickness of the ice, as long as we use the same projection and datum in geographical information systems.
So we're going to drill a hole through the ice with an ice auger on an electric drill, and then we're going to use just a tape measure to measure with a little T on the end of it, to measure the actual depth of the ice, and we'll use that as a validation of our other instruments that are much faster but not quite as reliable.
The light isn't very nice anyways either. So this is 155 and 132.
So 155 is the total thickness of the snow and the ice. And what was the other measurement?
132, that is in centimeters, that's the draft of the ice, the depth below the water level.
And up ahead they've already measured the snow thickness for us, so.
Today, as you know, we have made all these measurements to measure the ice thickness on the one hand and measure the depth of the ice underside under the water level and the height of the surface above the water level. And now we want to enter all the data into the computer to analyze it on the one hand, to look what the thickness distribution is and what the average thickness is and what the ratio between the surface elevation and the draft is, for example. And in addition, we want to plot this into a nice profile so that we can visualize it on the screen here. The water level is here at 0, and we started over on this side, over the level ice. You can see how nice and level it was, and then from a distance of 70 meters approximately, we came into the deformed ice, and our maximum thickness approximately was 4 meters draft plus half a meter of surface elevation, so 4.5 meters total thickness. Well, on the one hand, we are interested in what the thickness is here and what you can do with the thickness data, like by looking at the isostatic equilibrium and looking at these ratios of surface elevation versus ice thickness. We can calculate the density of the ice and compare this with the densities derived from the ice cores. And so we can just learn how you do these individual measurements and if they make sense in the end, how accurate they are.